Where is the S block in the periodic table? It's the first two columns or groups of the periodic table. This region of the periodic table is sometimes referred to as the S block because all the outermost electrons of these elements will occupy the s orbital. There are two columns in the s block because an s orbital can hold a maximum of 2 electrons. The metals in group 1 include lithium, sodium, potassium, rubidium, cesium, and francium. Note that hydrogen is not included here, as it typically does not exhibit metallic behavior. Here are some interesting facts about the group 1 metals. Lithium is the most abundant member of the family. Francium is radioactive, and its longest lived isotope has a half-life of only 21 minutes. Do you know the origin of the group name alkali metals? When group 1 metals react with water, they produce hydroxide OH ions. Hydroxide ions in water produce basic or alkaline solutions. In the presence of phenolphthalein, an indicator, the solution will turn pink as hydroxide ions formed react with phenolphthalein. Before we move on, let's review the electron configurations of the alkali metals. Lithium, with only 3 electrons, has a configuration of 1s2, 2s1. Sodium, with 11 electrons, has an electron configuration of 1s2, 2s2, 2p6, 3s1. Similarly, for potassium, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. They all have something in common. All the electron configurations end as s1. This is emphasized when the electron configurations are written in noble gas notation. All the alkali metals have electron configurations that end as ns1, where n is the highest occupied principal energy level. With such similar electron configurations, it's no surprise that the alkali metals have some very similar physical and chemical properties. We'll explore these further as we go through the module. The group 1 metals are the most reactive metals known. In fact, they are so reactive that they are never found in their elemental state in nature, only in compounds. Since they all react with water, they must be stored under oil, as shown in the illustration. They will even react with water in the air. The alkali metals are all shiny and silvery in appearance. They are so soft that they can be cut with a table knife, which is often surprising to students. Like all metals, they are good conductors of both heat and electricity. As shown in the diagram, they will form a dull oxide layer on their outer surface when exposed to air. This layer can easily be cut away to reveal the shiny interior. Recall that the alkali metals all have electron configurations ending as s1. The single valence electron for each of these elements is relatively loosely attracted to the nucleus. If this sole valence electron is lost, then the resulting ion is isoelectronic with the preceding noble gas elements, that is, having the same number of electrons as the preceding noble gas. Thus, the typical ion formed by alkali metal is a cation with a charge of +1. Let's go on and review some periodic properties as they relate to alkali metals. As you consider the group of 1 elements from top to bottom, atomic radius increases. This can be explained because as you move down the group, there is increase in the number of shells and therefore the atomic radii increases. The cations that form are in all cases smaller than the parent atom. Since there are fewer electrons, there are fewer electron-electron repulsions, and so the radius is smaller for the cation. For essentially the same reasons as we discussed with atomic radius, the cation radii for the group 1 metals increase from the top to the bottom of the group. As shown in the graphic, moving from left to right across a period, the alkali metals have the largest atomic radius of any element in the period. Try to answer this question on your own before you proceed. Where in the periodic table would you expect to find elements with the largest atomic radii? The largest atoms are found in the lower left-hand corner of the periodic table: cesium and francium. Recall that ionization energy is defined as the energy required to remove the outermost electron from an isolated gas phase atom. Since the valence electrons are significantly shielded from the nuclear charge, the ionization energies of the alkali metals are relatively low. In general, ionization energies decrease down a column, and the alkali metals are no exception, as shown in the graph. Enthalpy of solvation, or hydration energy, is the amount of energy released or absorbed when 1 mole of an ion is dissolved in a large amount of water. In general, as the ionic radii get larger, hydration energy decreases, and so the enthalpy of hydration decreases from lithium to cesium. One result is that lithium salts, unlike the salts of the other alkali metals, often form hydrates such as lithium chloride dihydrate. How can we test for the presence of alkali metals in a particular sample? One simple and qualitative test is the flame test. If a small amount of a metal salt is held in a flame, characteristic color changes can be observed due to the movement of electrons. Electrons get excited to higher energy levels from the heat of the flame and emit energy as light as they return to their ground state. For a quantitative test, atomic absorption spectrometry can be used based on the same fundamental principles. Let's look at the result of some flame tests. Lithium gives a cheerful candy apple red color. This yellow color is characteristic of sodium. You may have observed it if a boiling salt water sample spills over when cooking on a gas stove. Potassium flame tests emit a lilac-colored flame. Let's apply our knowledge to a problem. An explosion occurred in a chemical storage tank at Acme Chemical Company. An employee, while filing a claim for workers' compensation for injuries, states that the potassium nitrate being stored in the tank must have been responsible for the green flames he observed. Is the employee being truthful? We just learned that the presence of potassium gives a lilac flame. Therefore, we must conclude that the employee is not being truthful. Let's discuss some chemical properties of the alkali metals, starting with their reactions with oxygen. They all react vigorously with oxygen. They don't all form the same kinds of oxides though. Lithium reacts with oxygen to form a simple oxide, Li2O. Sodium forms sodium peroxide, Na2O2. The other metals all form superoxides. For example, CSO2. The oxides and peroxides that form from the alkali metals are typically white solids, as shown in the illustrations. They are basic anhydrides when placed in water. They will generate hydroxide ions, and thus basic solutions as shown in this reaction for lithium. The alkali metal superoxides, which only form with the larger alkali metals, are typically yellow or orange in color. Let's try some problem solving. What is the oxidation number of each element in the compounds? Lithium oxide, sodium peroxide, and rubidium superoxide. Recall that the sum of the oxidation numbers must be 0 for a neutral compound. For lithium oxide, since each lithium ion must have an oxidation number of +1, the oxygen ion must have a charge of -2. Using similar logic, since each sodium ion has an oxidation number of +1, each oxygen in the peroxide ion must have an oxidation number of -1. Rubidium here has an oxidation number of +1. So, each oxygen in the superoxide ion must have an oxidation number of -1/2. As was mentioned earlier in this module, the alkali metals all react with water. These reactions release hydroxide ions and hydrogen gas, as shown in the equation here. The reactions become increasingly more explosive down the column. The alkali metals all react with hydrogen. These reactions produce metal hydrides, which are ionic solids with high melting points. The alkali metals react very vigorously with the halogens. One classic example shown in the photo is the formation of table salt, or sodium chloride, from sodium metal and chlorine gas. The alkali metal halides are crystalline solids, as shown in the photograph. They have characteristically high melting points and are soluble in water. These are very stable compounds, as evidenced by their large negative enthalpies of formation. Since the alkali metals have a high tendency to lose their valence electrons, they oxidize readily. When they oxidize, they cause some other substance to become reduced. And so, we can say that alkali metals are good reducing agents. Remember, the substance that is oxidized in a redox reaction is called the reducing agent. The alkali metals will dissolve in liquid ammonia. As the metals dissolve, the resulting solution turns blue, as shown in the photograph. The blue color is due to ammoniated electrons, which absorb visible light. The solutions are paramagnetic, which means that they are attracted to an externally applied magnetic field. When allowed to stand, the solutions slowly release hydrogen gas as amides are formed. as shown in the reaction. When concentrated, these solutions turn a bronze color and become diamagnetic. Let's go on and discuss some uses of the alkali metals. Lithium alloys are used for a variety of purposes. An alloy with lead is used to make engine parts. An aluminium lithium alloy is used in airplane construction. And a magnesium lithium alloy is used to make armor plates. Lithium metal is used in some thermonuclear reactions and to construct various types of batteries. Liquid sodium is used as a coolant in fast breeder nuclear reactors. At one time, a sodium-lead alloy was used to produce organo-lead compounds, such as tetraethyl lead, which was used as an anti-knock agent in automobile fuel. The use of leaded gasoline was phased out due to the environmental pollution that it caused. Potassium has a variety of roles in biological systems. Potassium chloride, sometimes called muriate of potash, is used as an agricultural fertilizer. Potassium hydroxide is used to make soap and to absorb carbon dioxide. Cesium is used in the manufacture of photoelectric cells. In subsequent modules, we will discuss important compounds of the alkali metals and their biological roles. In some ways, lithium is more similar to magnesium, which is in group 2, than the other metals in group 1. This is sometimes referred to as a diagonal relationship, and it is due to the similarity in the ionic radii and the charge or radius ratios of these two elements. Compared to the other metals in group 1, lithium has a smaller radius and a higher charge or radius ratio, resulting in some anomalous behavior. In what respects is lithium atypical? It is denser and harder than the other members of its family, and its melting and boiling points are higher than the other alkali metals. Lithium is the least reactive element in the family, yet it is the best reducing agent. If you look at the table of standard reduction potentials, lithium is at the bottom of the table. This means that for the group 1 metals, lithium has the strongest tendency to oxidize. So, lithium is at the top of the activity series for single replacement reactions. Additionally, lithium chloride is the only alkali metal chloride that forms a hydrate, lithium chloride dihydrate. The chloride salts of the other alkali metals are anhydrous. In many ways, lithium is an exceptional alkali metal. Its compound with the hydrogen carbonate ion is not isolated in the solid state. It does not form an ethanide compound when reacting with ethine. When lithium nitrate is heated, the decomposition reaction results in lithium oxide. However, other alkali metal nitrates form nitrites when heated. This is shown in the equations. Lithium nitrate decomposes to form lithium oxide, nitrogen dioxide, and oxygen gas, whereas the decomposition of sodium nitrate yields sodium nitrite and oxygen gas. The fluoride and oxide salts of lithium are less soluble in water than the same salts formed from the other alkali metals. For example, only about 0.13 gram of lithium fluoride will dissolve in 100 grams of water. But it's possible to dissolve about 4 grams of sodium fluoride in 100 grams of water at the same temperature. The diagonal relationship between lithium and magnesium was mentioned earlier in this module. Lithium and magnesium have some notable similarities in their chemical properties. Both form nitrides, as shown in the reactions here. Both react slowly with water. Neither element forms compounds containing the superoxide ion. There are two other similarities worth mentioning about these two metals. First, their carbonates, when heated, decompose to form a metal oxide and carbon dioxide. Both the metals form water-soluble chlorides that are found as hydrates. Let's now talk about some important compounds of sodium. Sodium carbonate, sodium chloride, sodium hydroxide, and sodium hydrogen carbonate. Sodium carbonate, commonly known as washing soda, is a white, crystalline solid as shown in the photographs. It is typically found as a hydrate with 10 water molecules of crystallization, called sodium carbonate decahydrate. When heated, 9 of the water molecules of crystallization are typically removed, forming the monohydrate salt. Sodium carbonate is soluble in water, forming a colorless, clear solution. Above 373 Kelvin, it forms an anhydrous salt called soda ash. Most sodium carbonate is produced by the Solvay process, which was developed in the mid-1800s by Belgian chemist Ernest Solvay. This process, which has several steps, takes advantage of the low solubility of sodium hydrogen carbonate in water. Let's go through the steps of the Solvay process. In the first step, ammonium carbonate is synthesized from ammonia, water, and carbon dioxide, as shown in the reaction. Then, the ammonium carbonate formed in the first step is reacted with water and carbon dioxide to form ammonium hydrogen carbonate, as shown in the reaction given. Next, the ammonium hydrogen carbonate is combined with sodium chloride, and a sodium hydrogen carbonate precipitate is isolated. Upon heating, the sodium hydrogen carbonate decomposes to form water, carbon dioxide, and sodium carbonate. Finally, ammonia is recovered by reacting the ammonium chloride formed in step 3 of the process. Calcium chloride is the only byproduct of this entire process. Here's a practice problem for you to consider. Why can't we use the Solvay process to prepare potassium carbonate? Answer: potassium hydrogen carbonate is too soluble. It doesn't precipitate out of the solution when ammonium hydrogen carbonate reacts with potassium chloride. Sodium carbonate has a variety of household and industrial uses. It is used in water softening as well as in laundry and cleaning. It is used in the manufacture of glass and in the production of soap, borax and caustic soda, otherwise known as sodium hydroxide. Sodium carbonate is also necessary in the paint, paper and textile industries. Additionally, it is used in a variety of analytical techniques in the chemical laboratory. Sodium chloride is another important compound of sodium. Seawater is an important source of sodium chloride. When seawater is evaporated, it leaves behind crude sodium chloride, which contains several impurities including calcium sulfate, calcium chloride and magnesium chloride. Sodium chloride is commonly used as table salt and in the preparation of other compounds that contain sodium, such as sodium hydroxide, sodium carbonate and sodium peroxide. Like other ionic crystals, sodium chloride has a high melting point of 1081 Kelvin. The photograph here shows a halite crystal, which is a naturally occurring form of sodium chloride. As the green line in the solubility diagram shows, the solubility of sodium chloride is nearly independent of temperature. About 36 grams of sodium chloride can dissolve in 100 grams of water between 0 and 100 degrees Celsius. Another important compound that contains sodium is sodium hydroxide. In its pure form, it is a white solid, often sold in pellet form, as shown in the photograph. It is very caustic, so don't touch it. Sodium hydroxide melts at 591 Kelvin. It is deliquescent. It means that samples of sodium hydroxide left in the open will absorb water from the air and dissolve. Sodium hydroxide is very soluble in water. The preparation of a solution of sodium hydroxide is very exothermic. When preparing concentrated sodium hydroxide solutions, it is necessary to place the container in an ice bath. The solutions themselves are very basic due to the presence of hydroxide ions. Sodium hydroxide solutions will react with carbon dioxide to form sodium carbonate. Sodium hydroxide is used for a variety of purposes. It is used in the manufacture of soap, paper, and various textiles. It is used for refining petroleum, as a laboratory reagent, and in the preparation of fats and oils. Sodium hydroxide can be prepared by the electrolysis of brine solutions, that is, sodium chloride solutions, in the Kastner-Keller cell. A schematic diagram of this electrolytic cell is shown here. Recall that the cathode is where reduction occurs in an electrochemical cell. In the Kastner-Keller cell, mercury functions as the cathode. In the reduction half reaction, sodium ions combine with an electron to form a sodium-mercury amalgam. Oxidation occurs at the anode in an electrochemical cell. In the Kastner-Keller cell, a rod of graphite, a form of carbon, is used as the anode. In the oxidation half reaction, chloride ions form chlorine gas and release electrons. The sodium-mercury amalgam that forms at the cathode then reacts with water, releasing sodium hydroxide, mercury metal and hydrogen gas. Baking soda, or sodium hydrogen carbonate, is another important compound that contains sodium. When heated, it decomposes, releasing bubbles of carbon dioxide. It is used in baking to make the cakes and pastries rise. One way to prepare sodium hydrogen carbonate is through the reaction of carbon dioxide with a solution of sodium carbonate, as shown here. Sodium hydrogen carbonate is also formed with the Solvay process. Baking soda is used for a variety of purposes. It is used in baking, of course. It can be used as a mild skin antiseptic, as a household cleaner, as an ingredient in mouthwash and toothpaste, and as treatment for indigestion due to acidity, that is, as an antacid. It is also used in certain types of fire extinguishers. Both sodium and potassium have important biological roles. They are present in relatively large amounts in the human body. In an average adult male with a body mass of 170 kg, about 90 grams of sodium and 170 grams of potassium are present. Compare this with the other essential nutrients. Only about 5 grams of iron and 0.06 gram of copper. This reflects the important roles both sodium and potassium ion play in the human body. Sodium ions are found primarily in blood plasma and the lymph fluid surrounding the cells. Sodium ions play important roles in nerve signal transmission, regulating the flow of water into the cells, and the transport of sugars and amino acids into the cells. By contrast, potassium ions are the most abundant cations inside the cells. Potassium ions play important roles in activating enzymes, as well as the oxidation of glucose to produce ATP. Along with sodium ions, potassium ions are required for sending nerve signals through the body. In a resting neuron, the concentration of potassium ions is about 30 times higher inside the cell than outside. The concentration of sodium ions outside the cell is about 10 times higher than inside the cell. There are sodium ion channels and potassium ion channels in the cell membranes. When these become activated, sodium ions rush into the cell and potassium ions flow into the cell. The movement of sodium and potassium ions against their concentration gradients causes the polarity of the membrane to charge momentarily. As this moves down the neuron, the nerve signal travels through the body. The sodium-potassium pump, a transmembrane protein in cell membranes, uses active transport to move sodium and potassium ions across cell membranes against the concentration gradients. In doing so, the sodium-potassium pump breaks down ATP molecules. This process alone accounts for about 1/3 of the ATP used in animal cells. The alkali earth metals, which include beryllium, magnesium, calcium, strontium, barium, and radium, are found in group 2 of the periodic table. They all have 2 valence electrons. The alkali earth metals are not found as pure elements in nature, only in compounds. These elements, with the exception of beryllium, are known as alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the Earth's crust. The most abundant elements in group 2 are calcium and magnesium. They are the 5th and 6th most abundant elements in the Earth's crust. The other group 2 metals are significantly rarer in nature. Oxide compounds of group 2 elements are found in the Earth's crust. The alkali earth metals have similar properties because of their related electron configurations. Since they all have 2 valence electrons, they form cations with a charge of +2. Shown here are the electron configurations of 4 alkali earth metals. Notice how they all end as S2, showing those 2 valence electrons. The similarities in the electron configurations are even more apparent when written in noble gas notation. They all end as Ns2, where N is the highest occupied electron energy level. Because of their 2 valence electrons, all the group 2 metals form cations with +2 charges. By losing the 2 outermost electrons, they form cations that are isoelectronic with the nearest noble gas. Let's go on and review the periodic trends as they relate to the alkali earth metals. In general, atomic radius decreases from left to right in a period. In groups moving from left to right, outermost electrons enter into the same electronic shell. Therefore, size does not increase. Moreover, outermost shell is held more tightly by the increasing nuclear charge. Thus, we see that an alkaline earth metal has a smaller atomic radius than the group 1 metal in the same period. As shown in the graphic, atomic radius increases down a column because the electrons enter into new electronic shell and inner shells act as screens for outer electrons. Therefore, outermost shell is held less tightly by the nuclear charge. This pattern holds for the group 2 metals as well. Let's consider the ionic size trends. Cations are smaller than their parent atoms due to increased nuclear charge. As mentioned earlier, the group 2 metals typically form ions with a +2 charge. As shown in the graphic, the group 2 cations that form are significantly smaller than the neutral metal atoms. Recall that ionization energy is the energy required to remove an electron from a neutral, isolated atom. A typical equation representing this change is shown. In general, ionization energy increases from left to right across a period. the outermost electrons are held more tightly as the nuclear charge increases. In accordance with this trend, the alkaline earth metals have higher first ionization energies than the alkaline metals. The second ionization energy is the energy required to remove the second electron. Once the first electron has been removed, as indicated in the equation here, generally, second ionization energies are higher than first ionization energies. One interesting fact you should know: the second ionization energies for the group 2 metals, that is, alkaline earth metals, are lower than the second ionization energies for the group 1 metals, that is, alkali metals. This is because losing one electron for a group 1 metal gives it a noble gas-like electron configuration, and losing another electron from these cations becomes significantly less favorable. The alkali earth metals have relatively low ionization energies. However, reflecting their high tendency to lose electrons, ionization energies for the group 2 metals decrease down a column. So, we can describe the alkali earth metals as electropositive, and they become more electropositive down the column. Hydration enthalpy is defined as the amount of energy released when 1 mole of an ion is dissolved in a large quantity of water. As ionic size increases, hydration enthalpy decreases. Therefore, we observe a decrease in hydration enthalpy from beryllium through barium. The group 2 metal ions have larger hydration enthalpies than the corresponding group 1 metal ions. Many salts of the group 2 metals are found as extensively hydrated salts. For example, magnesium chloride and calcium chloride both exist as hexahydrates. Neither potassium chloride nor sodium chloride is found as a hydrate. However, let's discuss the physical properties of the group 2 metals. The alkali earth metals are silvery white, lustrous or shiny solids, although beryllium and magnesium may have a greyish cast to them. They are relatively soft metals, though harder than the alkali metals. Like all metals, they are good conductors of heat and electricity. The group 2 metals have higher boiling points than the group 1 metals due to their smaller atomic radii. Similarly, the group 2 metals have higher melting points than the group 1 metals in the same period, although the trend is not systematic. Flame tests are a simple, qualitative way to test for the presence of metals. By holding a sample of a metal salt in the flame and observing the change in the color. The heat of the flame excites the electrons to a higher energy level, and then the electrons emit light as they return to the ground state. Calcium salts produce a characteristic brick red flame. Strontium salts can be recognized by the crimson flame that results. Strontium salts are used to make fireworks that emit red light. Barium gives an apple green color to the flame. Why don't magnesium and beryllium produce colored flames? The electrons are held tightly by the nuclei in these elements, and so the flames do not excite them to higher energy levels. Magnesium, in fact, will ignite in the flame and react with oxygen, giving off an intense white light. Now we should discuss various chemical properties of the alkaline earth metals. In general, the alkaline earth metals are less reactive than the alkali metals. The group 2 metals form a variety of different types of compounds. Our focus is on the oxides, hydroxides, halides, carbonates, sulfates, and nitrates. We'll discuss each of these in turn. Magnesium and beryllium do not react with water because both the metals form an oxide layer on their surfaces. Calcium, strontium, and barium all react with water at normal temperature to form hydroxides. The reaction of calcium with water is shown here. These hydroxides have low solubility in water and are less basic than the group 1 metal hydroxides. In general, for the group 2 metal hydroxides, as the atomic number of the metal increases, the solubility, thermal stability, and basic character all increase. Beryllium hydroxide, unlike the other group 2 metal hydroxides, is amphoteric. It can act as both an acid and as a base. In the first reaction, beryllium hydroxide acts as a Lewis acid by accepting electron pairs from hydroxide ions. In the second reaction, beryllium hydroxide acts as a base with hydrochloric acid. Why do the group 2 metal hydroxides become more soluble down the group? Recall that metal cations increase in radius down a column. As internuclear distance increases, lattice energy decreases. So, less energy is required to separate the ions. The hydration enthalpy, however, decreases less dramatically. The net result is that the salts are more soluble in water. Beryllium and magnesium do not react with oxygen at normal temperature due to the formation of an oxide film on their surface. When burned in oxygen, the group 2 metals form metal oxides. For example, burning calcium in the presence of oxygen forms calcium oxide. Magnesium and beryllium, when ignited, will react vigorously in air, releasing a bright light. Both the oxide and the nitride will form when reacting in air, as shown here in the reactions for magnesium. Calcium, strontium, and barium also react in air to form oxides and nitrides. Beryllium oxide is essentially covalent in character. It is an amphoteric oxide, meaning it can act both as an acid and as a base. The other group 2 metal oxides are essentially ionic substances, and the basic nature of oxides increases from magnesium to barium. With the exception of beryllium oxide, the group 2 metal oxides are basic anhydrides. This means that they react with water to form metal hydroxides. All the group 2 metals can react with halogens, forming halide compounds. These reactions usually occur at high temperatures. For example, calcium fluoride forms when calcium metal reacts with fluorine gas. A sample of fluorite, a naturally occurring mineral of calcium fluoride, is shown in the photograph. The best synthetic route for preparing beryllium fluoride is to heat ammonium beryllium fluoride until it decomposes, as shown in the equation here. Beryllium chloride can be formed by reacting beryllium oxide with chlorine gas in the presence of carbon. Carbon monoxide is a byproduct of this reaction. The halide salts of the alkaline earth metals are essentially ionic in character, with the exception of the halides of beryllium. The beryllium halides are primarily covalent and thus are soluble in organic solvents. In the solid state, beryllium chloride has a chain structure. However, in the vapor phase, beryllium chloride forms a dimer. These dimers dissociate into monomers at very high temperatures. The halides of the group 2 elements are often found as hydrates, but these salts are complexed with fewer water molecules down the column. Thus, magnesium chloride is an octahydrate, whereas barium chloride is found as a dihydrate salt. These salts can be dehydrated upon heating, leaving anhydrous salts. It should be noted that beryllium and magnesium salts will undergo hydrolysis upon heating, though, in general, the fluorides tend to be less soluble than the chlorides because of the higher lattice energies associated with the fluoride salts. All of the group 2 metals, with the exception of beryllium, react with hydrogen to form metal hydrides. The reaction involving the formation of calcium hydride is given here. Beryllium hydride can be produced by reacting beryllium chloride with lithium aluminium hydride. The group 2 metals react with acids in a single replacement reaction, releasing hydrogen gas as a product. As a family, the alkaline earth metals have large negative reduction potentials. This feature reflects the strong tendency of the metals to lose electrons, otherwise known as oxidation. Since oxidation cannot occur without reduction, they can be considered good reducing agents. Beryllium has a lower reduction potential than the other group 2 metals because its cation is smaller and has a larger atomization energy. In liquid ammonia, the group 2 metals dissolve to form solutions with a deep blue-black color. Ammoniate salts of the general formula shown here can be recovered from these solutions. The carbonates of the group 2 metals are insoluble. They can be prepared by reacting soluble carbonate salts, such as group 1 or ammonium carbonates, with soluble salts of the group 2 metals. One such reaction is shown here. A photograph of the mineral calcite, a naturally occurring form of calcium carbonate, is shown here. The group 2 metal carbonates decompose upon heating to form the oxide and carbon dioxide, as shown for calcium carbonate here. The White Cliffs of Dover consist primarily of calcium carbonate. The thermal stability of calcium carbonate increases as the metal cation increases in size. Beryllium carbonate is unstable and must be kept in a carbon dioxide atmosphere. The sulfate salts of the group 2 metals are white solids that are heat stable. Beryllium sulfate and magnesium sulfate are water soluble. But the solubility of this class of compounds decreases down the column. This is because beryllium and magnesium ions have higher hydration enthalpies than the other metals in the group. The group 2 metal nitrates can be prepared by dissolving the carbonates in dilute nitric acid. This class of compounds repeats the pattern of the decreasing tendency to form hydrates down the column. For example, magnesium nitrate is found as a hexahydrate, but barium nitrate is anhydrous. When heated, all the group 2 metal nitrates decompose to form oxides, as shown in the equation for the decomposition of calcium nitrate. The alkali earth metals are used for a variety of purposes. We'll wrap up this module with an overview of the uses of these metals. Beryllium is used in many industries. It is used to prepare several alloys. The copper beryllium alloy is used to manufacture high-strength springs. Metallic beryllium is used for the windows of X-ray tubes. The inhalation of beryllium dust, vapor, or its compounds can cause berylliosis, a serious form of mental poisoning. Magnesium is also used to prepare alloys. A magnesium-aluminium alloy is used in the construction of airplanes. Magnesium metal is used in flash powders and flash bulbs for cameras. Milk of magnesia, a suspension of magnesium hydroxide, is used as an antacid. Magnesium carbonate is used as an ingredient in toothpaste. Calcium is used in the extraction of metals from oxides, when they are too difficult to reduce with carbon. Calcium, along with barium, has been used to remove air from vacuum tubes. The radioactive salts of radium are used in the treatment of cancer. In certain respects, beryllium does not behave like the other group 2 metals. In particular, the compounds of beryllium have a significant degree of covalent character and are easily hydrolyzed. This is due to the exceptionally small atomic and ionic radii observed for beryllium, as well as its high ionization energy and electronegativity compared to the other group 2 metals. Beryllium can achieve a maximum coordination number of 4. This is because there are a maximum of 4 orbitals in beryllium's outermost energy level, namely the 2s and 2p orbitals. The other group 2 metals can utilize the d orbitals to have a coordination number of 6. Beryllium oxide and beryllium hydroxide are amphoteric substances, meaning that they can act as both acids and bases. For example, the first reaction shows beryllium hydroxide acting as a base, neutralizing sulfuric acid. The second reaction shows beryllium hydroxide acting as an acid to form the complex ion berylate. In several ways, beryllium behaves more like aluminium than the other group 2 elements. It's worth being familiar with the details of this diagonal relationship. First, the beryllium ion and aluminium ion have similar charge to radius ratios as shown here. Neither beryllium nor aluminium reacts readily with acids due to the oxide film that both the metals exhibit on their surface. The hydroxides of both the metals dissolve in solutions of excess hydroxide to form complex ions. In the vapor phase, both beryllium chloride and aluminium chloride form chloride-bridged structures. Both the chlorides are soluble in organic solvents, reflecting their essentially covalent character. Both the chlorides are strong Lewis acids, acting as electron pair acceptors in chemical reactions, as shown in the reaction given here. Both the chlorides are used as catalyst in the Friedel-Crafts reaction shown here. Both beryllium ions and aluminium ions form complex ions. Next, we will consider some important compounds of calcium. Calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. Calcium oxide, which has the chemical formula CaO, is commonly known as quicklime. Calcium oxide is a white, amorphous solid with a melting point of 2870 Kelvin. To prepare calcium oxide on an industrial scale, limestone or CaCO3 is heated in a rotary kiln at 1070 to 1270 Kelvin. At these conditions, calcium carbonate decomposes to form calcium oxide and carbon dioxide. The carbon dioxide is removed continuously to drive the equilibrium to the products. Quicklime absorbs carbon dioxide and moisture from the air, as shown in these reactions. When carbon dioxide is absorbed, calcium carbonate is the product. Slaking of lime, shown in the second reaction, refers to the process in which, when a limited amount of water is added to a lump of lime, it breaks up and results in the formation of a suspension of slaked lime along with the liberation of heat. This reaction also shows that calcium oxide is a basic anhydride, since its reaction with water forms calcium hydroxide, which is alkaline. Calcium oxide is a basic oxide and thus can combine with acidic oxides at high temperature. For example, reactions with silicon dioxide and phosphorus pentoxide are given here. Calcium oxide has a number of industrial uses. It is necessary for the manufacture of cement and is the cheapest form of alkali. It is used to produce sodium carbonate from sodium hydroxide, also known as caustic soda. It is used in the purification of sugar and in the manufacture of various dyes. Calcium hydroxide, another important compound of calcium, is commonly known as slaked lime. It is a white, amorphous powder that can be prepared by adding water to calcium oxide. Calcium hydroxide is only sparingly soluble in water. Aqueous solutions of calcium hydroxide is commonly called lime water. Milk of lime is the common name for suspension of calcium hydroxide in water. Lime water provides a simple test for the presence of carbon dioxide. Lime water turns milky when carbon dioxide is passed into it. A precipitate of calcium carbonate forms in this reaction, as shown here. If more carbon dioxide is passed into the above solution, the precipitate dissolves and forms calcium hydrogen carbonate. Milk of lime, a suspension of calcium hydroxide in water, reacts with chlorine gas to form calcium hypochlorite, the main component of bleaching powder. Hypochlorite ion is a good oxidizing agent. Calcium hydroxide is an important industrial chemical. It is used in the preparation of mortar and to make whitewash. It is necessary for making glass as well as for the tanning of leather. As was just discussed, it is used in the preparation of bleaching powder. It is also used in the purification of sugar. Calcium carbonate occurs naturally in several forms, including limestone, chalk, and marble. In its pure state, it is a white, fluffy powder that is nearly insoluble in water. Upon heating, it decomposes to form calcium oxide and carbon dioxide. Calcium carbonate can be formed in two ways. The first process involves passing carbon dioxide through slaked lime, as shown here. Alternatively, sodium carbonate reacts with calcium chloride to form calcium carbonate and sodium chloride. This is shown here. Calcium carbonate is used for a variety of purposes. It is well known as a building material. It is necessary in the manufacture of quicklime. It is used industrially as a flux in extracting metals from ores and in the manufacture of high-quality paper. It is also used as an antacid. Calcium carbonate is an ingredient in toothpaste and chewing gum and is used as a filler in cosmetics. Plaster of Paris is a hemihydrate of calcium sulfate. Plaster of Paris is formed when gypsum or calcium sulfate dihydrate is heated to 393 Kelvin. The decomposition reaction is shown here. If gypsum is heated above 393 Kelvin, anhydrous calcium sulfate or dead burnt plaster will be the product. When water is added to plaster of Paris, it forms a plastic, malleable mass that hardens in 5 to 15 minutes. Plaster of Paris is used in the building industry. In medicine, it is also used to prepare casts to set bone fractures. It has applications in dentistry too. Besides, plaster of Paris is used for ornamental work, such as the ceiling medallion shown here, as well as statues. Cement, or Portland cement as it is often called, is another important compound of calcium. The raw materials for making cement are limestone and clay. The composition of cement is not fixed. Portland cement typically contains 50 to 60% of calcium oxide and 20 to 25% silicon dioxide as its main components. Cement also contains 5 to 10% aluminium oxide, 2 to 3% magnesium oxide, 1 to 2% iron 3 oxide, and 1 to 2% sulfur trioxide. In good quality cement, the ratio of silica or silicon dioxide to alumina or aluminium oxide is between 2.5 and 4. The ratio of lime or calcium oxide to the total oxides of silicon, aluminium and iron should be as close to 2 as possible. Cement clinker is formed when clay and lime are strongly heated. They fuse together to form cement clinker, shown in the photograph. To form cement, 2 to 3% gypsum by mass is added to the cement clinker. This mixture is then ground to make cement. Ingredients that make up the bulk of Portland cement include dicalcium silicate, making up 26%, tricalcium silicate, contributing 51%, and tricalcium aluminate, contributing 11%. Cement sets when it is mixed with water to form a hard mass. The molecules of the components get rearranged and hydrated. The presence of gypsum slows down the setting process so that it gets very hard. Cement is used to make concrete and reinforced concrete. It is used in plastering as well. It is best known for its use in the construction of bridges, dams, and buildings of all sorts. Both magnesium and calcium play important roles in biological systems. An adult human body contains 25 grams of magnesium and 1,200 grams of calcium. Compare this with only 5 grams of iron and 0.06 gram of copper. Let's go into these important functions in more detail. Phosphoryl transfer enzymes, which use ATP in phosphate transfer, use a magnesium ion as a cofactor for enzyme function. An illustration of one such enzyme is shown here, with the magnesium ion shown in green. Chlorophyll is the main pigment in plants that absorbs light for photosynthesis. The porphyrin ring in chlorophyll contains magnesium. Bones and teeth contain about 99% of the calcium in the human body. Bone, which is alive, with a complex structure, is continuously being solubilized and redeposited in the body. Approximately 100 milligrams of calcium are dissolved in 1 liter of plasma. This concentration is regulated by the action of 2 hormones, calcitonin and parathyroid hormone. Calcium ions play an essential role in muscle contraction. A diagram of the sliding filament theory of muscle contraction is shown here. Calcium ions also play an important role in blood coagulation. Calcium ions are essential for the transmission of signals between nerve cells. Calcium ions are important for cell signaling and for various physiological processes. Calcium channels regulate the transportation of calcium ions across cell membranes.